Hi, sorry for sudden interruption. It was just my battery went out. So on the finish of that problem about yes, choice of committees, so we actually had on the bottom of the page here 40 for one choice, then we had 30 for the choice with 2 women on the committee, and with 3 women on the committee we have 4. We just add them up, and the result was 74. So that was just the part that was cut out, right? So that that you have the end of that problem recorded. All right. Now I'd like to show you one more example that is somewhat confusing if you just look at it carelessly, and that's example 434. How many strings? How many beat strings? So 0 ones. Beat strings of length 10 contain exactly 3 ones. So 3 ones and 7 zeros. So what's a little bit confusing in this problem is that when you have a string 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, just if you look at it carelessly, one would say, wait a minute, order is important for a string because they are zeros and ones. So order is important. It's important if I put 1 here or I put 1 here. But basically, we have tons of repetitions here, so we cannot use our CNR formula or PNR formula because order is important. One would say it should be PNR. But basically, there are tons of repetitions here, so we cannot call any of our formulas. Actually, if you rephrase the question, then the answer comes very easy. Answer is very easy. So what? I need to put 3 ones. Where do I put them? Wherever I want. I need to choose 3 spots to put ones, like these 3. When I make that choice, that's it. Configuration is there. I put ones there, zeros everywhere, and that's it. So my only goal in this construction, my only design is choose 3 out of 10. Who gets chosen first? Doesn't matter. In all of them I put 1, no matter if I choose this first and then this. So order is not important. I'm choosing out of 10 spots. I choose which 3 will host ones. And the order is not important. Who was among them chosen first? So that's C10-3, and then that's C10-9-8, 3-2-1. So that's what, 120. So that's how it works. So you need to phrase it properly, and then it will come again. We'll do one problem, and then we'll make a little theorem about it. And this example says the following example. In how many ways? Can we reorder the letters of the word hullabaloo? So what's happening? None of our configurations works because there are repetitions. And let's count those repetitions because that will be crucial. So it will be 3 L's. 1, 2, 3. There are 3 A's, I think. No. Who else? There are 3 L's. No, there are 2 A's. Okay. There are 2 O's. And these are the only repetitions. H, U, and B are just regular, just repeating ones. Altogether 10, 3, 2, 5, 7, 3, 10, that's exactly what it is. So here's the solution. I will pretend that those L's are different. So maybe in different colors. One blue, one green, one green, and one red. So now they are kind of three different letters. I do the same with A's and with O's. So what would that be? I would get 10 factorial. Why? Because I have 10 different objects and I can shuffle them in 10 factorial ways. But then what? Every permutation of L's, when I change red comes here, blue comes here, green is actually not changing my configuration because on black and white printer, black and white sees it as the same word. So, how many of those permutations among L's can I do? 3 factorial. So I have to divide because I have 6 repetitions of each word because of different ways I shuffle L's. The same thing for O's, so times 2 factorial. The same thing for A, 2 factorial. That's it. And actually, so that's the and equal, that's a number. To have complete sentence, and here's the theorem. What's the name? Theorem 432. So suppose that we are rearranging the list of n objects consisting of n1 occurrences of object 1 n2 of object 2 and k of object k. In this theorem they are allowed also to be ones, so I would count h, u, and v as well, although 1 factorial is 1, we never count that. So n1 plus n2 plus nk is n. So each of those appearances, that's the total number of letters. Then we call that p, n, n1, nk. As I said, ones in that list are here, but we don't usually write them, is n factorial or n1 factorial, n2 factorial, nk factorial. That's exactly what we concluded here. All right, that finishes the combinatorial aspect of this section. And now we want to go to the properties of combinations. And they are important for a few reasons. First, they help us to calculate them faster. They are used in other areas of mathematics. For us, particularly, they are important because we'll use them in section 4.4. So, properties of combination. Property 1. N choose R equals N choose N minus R. What's this? So first, why would we care? That's always the most important question. Why are we better when we know this rule? Number 2 is what is the meaning, and then configure combinatorially, and then what is the just rigorous proof. So here's why is this property 1, prop 1. Important, here's for what? Suppose I need to calculate 7, choose 5. And generally I can write it. How did I tell you to do that? 5, 4, 3, 2, 1. Here's 7, 6, 5, 4, 3. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Balanced. But then what happens? 5, 4, 3 cancel. And actually I get this. 7 times 6. over 2 times 1, which is basically what? 7 just 2. 5 and 2 are complementary with respect to 7, so which one I use doesn't matter. Of course, smaller one is better. So instead of 7, 5, I should have known immediately that I can use 7, 2 and get it much quicker. Why is this logical? Why is it logical that this is correct? Because here it is. If I have 7 people in the room, and I need to choose 5 to be in, on the team, on the bus, whatever. What about it's the same thing as among those 7 people, choose those 2 that are out. Because once I choose who is out, everybody else is in. So those that are out, I can choose 7, choose 2 ways. Those that are in, 7, choose 5, but those are determining the same stories. Once I know who's in, then immediately I know who's out and the other way around. That's why the number of configurations is the same. Calculationally, what would be the proof? What? N choose R by definition is n factorial, r factorial, n minus r factorial. What is n choose n minus r? Basically the same thing, but now r, because r came first, now n minus r comes first. Then I go n minus r. But that n minus r is just r, so I get n factorial over n minus r factorial, just in different order. So the same thing, just in different order. So that's what I said a minute ago. In, out, and this is out, in, the same story. All right, that's the first property. Second property is just something to be aware of so that you're not confused. It's very simple. I'll put it here on the side, property 2. N choose 0 is 1, and n choose 1 is just n. Just write the form. So this one is just n over 1, because just one member, and that's very easy. Combinatorially, if I have n people and I choose 1, I can choose either one of them in n different ways. This might be a little trickier. Why? Because what is n choose 0? Calculation, it's n factorial over 0 factorial, n minus 0 factorial. N minus 0 is just n, so these cancel. But how much is 0 factorial? Maybe I never told you that. 0 factorial is 1. That's by math convention. Conventional mathematicians, the 0 factorial is 1. So this is 1. So that was very simple. Combinatorially, I have 10 people. I need to choose nobody to go on the bus. So in how many ways can this story be executed? One way, just nobody gets on the bus goes empty, that's it, that is the story. So how many configurations? One configuration. All right, and now the most famous property among all the properties of combinations, and that is Pascal identity. We need that for our section forward. We can really use it very nicely, but let me put it on the board. Pascal identity. It says the following: n choose r plus n choose r plus 1 equals n plus 1 over r plus 1. What's this telling us? In next section, when we build Pascal triangle, you will see even nicer how this looks geometrically. But generally what it says, that here we have n objects. So here we choose r of them, here we choose r plus 1 of them. Total of those two counts is the same as one count, where we have n plus 1 object and choose r plus 1. There's no reason in the world to see this really happening, or maybe there is, I don't know. Not obvious, not very simple one like the previous ones, but it's really true, and we will see that calculation. So proof. Crucial idea will be something that I mentioned in the previous section, and that is, if I have like r plus 1 factorial, that's r plus 1 times r minus 1, 3, 2, 1. But this is actually r factorial. So r plus 1 factorial can be, I start making factorial, all the others are still kind of boxed in that construction. So here it is, my left side equals, I use definition, n factorial over r factorial n minus r factorial. By the way, this a few times I asked for this proof as a problem on the exam. And n factorial r plus 1 factorial times n minus r minus 1 factorial. And then what? I just want to add these two fractions building common denominator. And here is how I'll do it. Let me here, you see here is r factorial, here is r plus 1 factorial. This guy has an extra member, so let me split that. So n factorial, r factorial, plus n factorial. Using this property, I will write r plus 1 factorial as r plus 1 times r factorial. The same way here, this guy has an early start, has an extra member with respect to this one. So I write it using the same property as n minus r times n minus r minus 1 factorial. Because this is the number preceding n minus r minus 1, the same way as r plus 1 precedes r. And I lost my n minus r minus 1 factorial. When you look at these numbers, this is the same as this. This is the same as this. These two guys are not the same. So what do I do? Common denominator. This guy needs r plus 1, so I'll put r plus 1 on the bottom. And on top. This guy needs n minus r, so I put n minus r on top, and n minus r on the bottom. So that's just basic algebra. That's it, we are done. Just a little, algebra, but everything is there. So basically now they have the same denominator. I will start packing back. So r factorial times r plus 1 is r plus 1 factorial, the same way as we opened it from before. And n minus r times n minus r minus 1 factorial is n minus r factorial. That same disciplines. On top, both guys have n factorial, so I'll factor it out. And who's left? R plus 1 plus n minus 1. And then what? R and R cancel. So what do I have on top? N plus 1 times n, which is n plus 1 factorial. What do I have on the bottom? R plus 1 factorial. And in order to match definition, I will write it as n plus 1 minus r plus 1. 1 and 1 cancel, so they're the same thing. So what's this? I have a number, here I have other number, here is their difference. That's exactly the definition of a choose coefficient, so that will be n plus 1 over r plus 1, which is our right side. As I said, I just wanted to have this ready for our next section. In our next section, we will frequently use this very interesting and nice identity. Once again, it's called Pascal identity, and you're probably familiar with Pascal triangle, and this is the crucial identity that supports the structure of that triangle.